Welcome to the second season of Science Actually, a podcast by Imperial College London students and staff. We're delighted to have you back for a new exciting topic, the science of the future. Tag along as we ask Imperial's experts to give us a glimpse of what's ahead of us.
Hi, and welcome to this episode of Science Actually podcast. My name is Eva, a second-year biological sciences student from the Science Actually team. And in this episode, we will explore Imperial's research into sustainable materials. To do so, I have with me three expert guests. Our first guest is Dr. Charles Romain, a lecturer in the Department of Chemistry. We also have with us Dr. Kun Yang Lee, a reader in polymeric materials in the Department of Aeronautics. And finally, Professor Magda Titirici, a chair in sustainable energy materials and a member of the Department of Chemical Engineering. The main question we will address in this episode is, what is the future of sustainable materials? So our first guest, Dr. Romain, carried out his studies in France, where he obtained a PhD from the University of Strasbourg. His research group at Imperial is interested in developing sustainable polymers by using renewable resources and improving material end of life, amongst other areas. Dr. Romain, thank you for joining us and for starting us off in this episode on the fascinating subject of sustainable materials. Could you please introduce the topic for us by explaining what bioplastics are?
Thank you, Eva, for the kind of introduction. Plastics, I would say, is a solid material that is made of polymer, which are large macromolecules. We can compare that to a kind of cocktail of molecules, or I will say with some ingredients give the properties of the material you want. So, for example, some plasticizer or other additives. This polymer, which is the main ingredient of plastics, made from a small building block, what we call a monomer, and that monomer can be bio-based or obtained from fossil sources, or can be petro-based. So, resources, monomer, polymer, plastics. So what are bioplastics? How do they fit in this picture? So bioplastics, by definition, I would say, are plastics that are either bio-based, made from plants, or degradable, non-durable, or can be both bio-based and degradable. So you can already see that definition of bioplastic is quite ambiguous. I keep using the word degradable, but by degradable, I refer to plastics that are both compostable and biodegradable, and there is a big difference between home compostable and industrially compostable. So that is a general misconception.
So your lab group is looking at designing methods to obtain sustainable polymers from renewable resources. So could you explain what you're doing in your lab and what kind of category of plastic you're looking at?
And in my group, we mainly focus on the conversion of monomer to polymer. So trying to identify new chemicals that could be used as monomers, and keeping in mind the sustainability aspect, we try to look at molecules that could be obtained from abundant large feedstock. So obtained from lignin, from cellulose, from what we call second generation feedstock. Typically, so it's feedstock that do not compete with food, but still use arable land. So, for example, wood, grass, cellulose, lignin. One of the main challenge, I will say, is it's not always easy to predict what will be the properties of the polymer, especially if we want to predict the degradability of the material, the end of life. So, having something useful without having to compromise on the sustainability, I would say, is the biggest challenge for us.
Right. So do you think that we'll ever be able to either find or make, we can even design it, this ideal kind of monomer?
I'm very optimistic, and that's why we do research. We learn from previous experience, and we try to develop better material. Sustainability, we need to consider lots of different aspects of sustainability. Not only the using the monomer and the resources being bio-based, but how you produce it, how people use it, and the end of life. In the future, think about new process, new methodology, where you can go from the polymer to chemicals or the same constituents, the monomer as a building block, and allow you to make again the same polymer or eventually different one. But I think there is a lot of room for improving the technology, improved polymer end of life.
Right. So to finish off, I just wanted to go back on what you said earlier. So you've investigated obtaining chemicals from renewable resources like cellulose and lignin. So would you mind elaborating on this and why this might be a good path to go down?
The monomer you get from cellulose and lignin by nature are very different from the one you get from fossil resources. Hydrocarbon from fossil resources, you mainly get hydrocarbon, so carbon, hydrogen. When using renewable resources or monomer from renewable resources contains oxygen. So by nature, there are different monomer. And I think the idea is to take the versatility or the diversity offered by nature to access to new original monomer and get to new polymer. That is the exciting part.
Great. Lovely to hear that. Thank you so much, Dr. Romain, for joining us on this podcast.
Thank you.
This discussion around lignin and cellulose brings us nicely to our next guest, Dr. Kun Yang Lee, and his research. Dr. Lee completed the majority of his studies at Imperial, including a PhD in composite materials. Since 2015, he has worked at Imperial as a lecturer and senior lecturer in composites manufacturing, and most recently has become a reader in polymeric materials. Dr. Lee's Future Materials Group focuses on developing materials for a sustainable, resource-efficient, low-carbon and low-waste future around lignin and cellulose. Dr. Lee, thank you for joining us. Our polling team asks you, how does this technology work in layman terms?
So think of it as trees being the ideal composite being perfected by nature. Essentially is cellulose embedded inside lignin, and you have something that's stable, completely sustainable, taking carbon from the atmosphere and nutrients from soil and grow into this beautiful structural product. What we're interested in essentially is to be able to learn from trees essentially and reconstruct lignin and cellulose, not as only as a structural materials, but as flexible packaging, something stable, flexible that will be able to replace our fossil-derived plastics.
Right, so just a quick clarification. What is the difference between lignin and cellulose?
So cellulose is a linear molecule, the reinforcing molecule within trees. Lignin is the surrounding matrix that surrounds cellulose, that protects cellulose. And lignin itself is a rather cross-linked aromatic compound, and this is actually what makes trees difficult to process. The lignin itself is so cross-linked that it's very difficult to deconstruct them. Any deconstruction of trees down to lignin and cellulose will almost inevitably destroy the lignin structure, leading to a rather sort of difficult to process mass of product.
Would you like to tell us more about your research group and the work you're doing around lignin and cellulose?
Sure. Specifically on the topic of lignin and cellulose, this is where the flexible packaging research area of my group comes in. What we're working on essentially is to try and reduce that particular deconstruction or find a way to reassemble the deconstructed lignin back to as close to pristine lignin as possible while having the cellulose inside. So think of it as reinventing trees or remanufacturing trees from trees.
Right, and another very relevant question has been asked by our polling team is, could we extract these biomass materials from food waste?
Definitely. So we do have a lot of problems with food waste, and the biggest problem with food waste is that they are typically contaminated with other waste. So think of bones from your meat, right, or even meat themselves that gets dumped into the same rubbish bin. So we are working on a process whereby we can isolate out only the vegetables side of the composition of your rubbish bin. So these are the lignin and the cellulose, or just the cellulose themselves, so that we can then subsequently reprocess these vegetables, if you will, or cellulose or lignocellulosic materials into flexible films, into any useful feedstock for future packaging applications.
Right, so you talk about using trees to make these resources, but would this not contribute to more deforestation? Where would you get these wood materials from?
So trees is a example that I'm using. In reality, you could actually use any biomass. So food waste is something you talked about, so that will work out nicely. Grass, there are some very, very fast growing grass, especially in the UK, that you can actually use as your lignocellulosic source to make these products. Overall, in the world, we do have enough biomass to produce energy and to produce materials. The question here is whether these biomass, are they suitable to be converted for flexible packaging applications, or are they more suitable to be used for energy? And this is still a big question that people are wondering. Energy versus plastics.
Right, so keeping that in mind, do you believe that cellulose and lignin are like the way to go and that they could be useful and realistic in the near future?
It is definitely the one of the easiest way to move forward. So trees, grass, lignin, cellulose, the whole structure has been designed by nature essentially to capture carbon, converting carbon into a beautiful product. And it is a carbon sink, if you will. So imagine a process whereby you grow biomass, capturing the carbon, converting this biomass into a sort of flexible packaging product. You use it. At its end of life, you will then put it into landfill. It biodegrades, turns back into carbon again. You then grow more biomass to capture this carbon. You have a perfect circular economy for you to just keep recycling carbon without you actually putting in the extra effort of specifically capturing artificial carbon, if you will, that's generated from power plant, for example. So there is actually this beautiful solution that using trees as the natural carbon sink, like what our ancestors have been doing about 50 years ago, 100 years ago.
Do you think this could work in the current world?
It will work. It is currently working in smaller items. The bigger question here actually lies with how are we going to convert the trees, the lignins, the cellulose into flexible packaging. That is a much more challenging research question to ask. Once you get to that flexible packaging, deconstructing these would derive biomass-derived flexible packaging into CO2 and water. That is actually an easy bit. And once it turns to CO2 and water, it's just growing more trees to capture the carbon again.
That's super interesting. One last question for you, Dr. Lee. What do you think we would need to do to be able to address the main challenge that you've just brought up?
So the biggest challenge with using lignin and cellulose is the following. The isolation of a suitable lignin from a suitable lignocellulosic source. The lignin isolated from one particular process, from one particular species, is different from another process from another species. The cellulose itself is different as well. And the second biggest challenge in this case is how do you reassemble the lignin and back into its native form, the cross-link form. The last thing that we would have to address, the flexibility. So trees, if you know, it's difficult to bend. So that cross-linked nature makes it extremely brittle. And what we do not want in a flexible film is that brittleness. How do we make a cross-linked lignin flexible, ductile? Now that's an open question that we have been trying to answer for the last sort of 20-something years or so. Not quite there yet. With the right combination of plasticizers, with the right degree of cross-linking perhaps, we might be able to get there sooner than we expect.
That was super interesting. It's an area of research that we don't hear about much.
But hopefully it will inspire more people to do things. Obviously, some of the stuff that I said are so high level that it's actually very difficult to allow people to believe in, but I have to make it as simple as possible. But you did raise the point that trees is a good point.
Great. Thank you so much, Dr. Lee, for telling us more about this area of research and for joining us on this podcast.
No problem. Thank you.
So sustainable materials and renewable materials, as explained by Dr. Romain and Dr. Lee, can and are being used to provide alternatives to plastics. However, they can also be used to address the issue of resources in sustainable energy technology. This is one of Professor Titirici's many areas of expertise. Since 2019, she is the chair in Sustainable Energy Materials at Imperial College. Currently, one of her areas of research addresses the resources in sustainable energy technology and where these will be sourced in the future when material availability changes. Professor Titirici, thanks for joining us today. Can you expand on what you're working on regarding the sustainability and renewability of materials going into these energy technologies?
Yes, the materials that are used today in our emerging energy technologies, whether it's batteries or hydrogen or solar panels, they're all considered critical, and they are listed as critical by the European Union. On one hand, to their limited supply chain, but mostly because of their increasing economic importance and the way they are distributed around the globe, being located only in certain areas.
So, a concrete example that will echo with our listeners involves lithium-ion batteries, which are used in everyday electronics and devices, such as a phone or a laptop. So, based on the research that you're carrying out, are these truly sustainable?
So, lithium-ion batteries, they are a fantastic discovery, but in their current form, they are not truly sustainable. The biggest challenge with lithium-ion batteries is the availability of the supply chain. This includes lithium itself, which is used in the electrolyte, and lithium in the form of brine, which is easier to process for batteries, is only located in a few areas of the globe, mostly South America, Bolivia, Chile, and Argentina. Now, equally, at the cathode, we use either cobalt and nickel. These are also critical endangered elements. Cobalt is primarily mined in the Democratic Republic of Congo, using often child labor and unethical mining practicing. Nickel is another vital material at the cathodes in batteries as we are moving towards nickel-rich chemistries. Most of the nickel grade for battery is located in Indonesia, and there's a huge interest in battery producers going and mining there also in not the most ethical possible way. At the anode of a lithium-ion battery, there is graphite, and this is also listed as critical because of its geographical location, primarily being available in China. And of course, as we know, China is one of the biggest battery producers, so that means they will have to rely on China to have availability to this important supply chain. So yeah, there's a problem in general with the criticality of materials for batteries, and this is what I'm trying to address in my research, moving away from these critical materials.
Mm-hmm. And what are you currently looking at to replace these materials?
So we are firstly looking at alternative battery technologies to lithium-ion. In particular, we are looking at sodium-based systems, so sodium-ion batteries, with the advantage the sodium is way more abundant and evenly distributed around the globe. And we are also researching aluminium-based batteries, with aluminium being the most abundant metal on Earth and also the most recyclable metal. In addition, we're looking on replacing the components of the anodes, the graphite, with a form of disordered carbon, which you could produce from any biomass, bio-waste, whether it's food waste or plastic waste. So we're looking into a circular type of economy of, upcycling waste into high-grade electrode materials. And we're looking at the cathode and moving away from nickel and cobalt and replacing them with more abundant elements such as iron or manganese, which are very suitable for these new emerging technologies, particularly for sodium-ion batteries.
That's incredibly fascinating. Another example that I wanted to bring up, and that's relevant, is hydrogen. So it's big on the agenda of the UK government, and they have ambitious plans, notably to use it in their transition to net zero. So are there any challenges of implementation at this scale with hydrogen?
The UK government has very ambitious plans for hydrogen, and it will be a vital part of our transition to net zero, and it will be used to decarbonize the UK economy across sectors. The UK wants to use its enormous power for wind, in particular offshore wind, to generate green hydrogen at low cost. So there is a scaling challenge, and mostly hydrogen today is done using water electrolysis. There are different types of water electrolysis. The most efficient system here is proton exchange membrane water electrolysis. This reaction is quite sluggish and happens with high over potentials, meaning that actually you will need a higher electricity input that what you theoretically calculate. And so that makes this technology quite costly. In addition to lower this over potentials, only one metal can do it very well, and this is iridium oxide, which is, again, a very scarce and critical element, is actually a byproduct of platinum mining, with platinum itself being scarce. So what we're looking in this technology is trying to come up with more sustainable, abundant catalysts than iridium oxide. But at the same time, we're also looking at replacing water altogether in electrolysis with actually the electrolysis of waste that have quite a lot of protons. And instead of oxidizing water at your anode, you then partially oxidize this bio-waste to produce high valuable chemicals, at the same time producing hydrogen at the cathode. And so this is advantageous because you decrease the cost of hydrogen. The over potentials here that I talk are much lower for this partial oxidation of biomass or bio-waste. You can also replace the iridium oxide in these materials with things like manganese, for example. And again, you produce two valuable things instead of one, hydrogen and high-value chemicals.
So using what you've mentioned, using bio-waste or plastic waste in this process, has this been implemented yet? And if not, why not?
No, so this is a very new and emerging technology that is just studied at lab scale at the moment. So our plans are really to look at the viability of this new way of producing hydrogen at scale. First of all, using some prediction, modeling combined with life cycle assessment and techno-economics to first understand on paper via calculation if this is viable, and then trying to move away to larger scales electrolyzers for this technology. The good thing is that the electrolyzer itself is very similar to a water electrolyzer, so it shouldn't be too difficult to upscale it.
Kind of incorporating all of this, to conclude our episode, what is the future of sustainable materials as you see it?
So I think the future of sustainable materials goes in three directions. First of all, we need to develop a circular economy. The technologies that we have today, and that includes lithium-ion batteries, will need to become more recyclable. Second, substitution is very important as well. So trying to create alternative materials to these precious metals as we do based on more widely available resources is also very important. And finally, potentially the third one is discovering new resources for these critical materials and mining them in a more sustainable and ethical manner.
So thank you so much, Professor Titirici, for this eye-opening discussion.
You're welcome. Thank you very much.
Thanks to our three guests, we now have a little more insight into the state of the field of research into sustainable materials. Lignin and cellulose may be the way to tackle food waste and flexible packaging issues, yet challenges still remain in this area. Another promising area is sustainable energy. Even though lithium-ion batteries are a fantastic solution, there is still work to be done in making them truly sustainable in their construction. We are confident that the labs at Imperial will find a solution soon. Thank you to our guests, and thank you for listening to this episode of Science Actually podcast.